Hello, hello. Some more Calc 3 videos right now, and what we're going to talk about is the acceleration vector and tangential and normal components of acceleration. Um, if you're following along in your notes packet, this looks like it's page 25, but who knows, if I use this video again, it could be on a different page. But find the page that has your acceleration vector and your tangential and normal components of acceleration, and we're going to get started. Previously, we talked about capital T and capital N, which were your unit tangent vector and your principal unit normal vector. These components of acceleration have a lot to do with that, so this is follow up there. So what's an acceleration vector? Well, if r of t is the position vector for a smooth curve, and n exists, the principal unit normal vector, and then the acceleration vector a of t lies in the plane determined by t and n. Okay, so when you have an acceleration vector, what it's telling you is it's in the same plane as your tangential and principal unit normal vector, your tangent and principal unit normal vector. Because when you think about a path in space, honestly, I can use this thing right here. There's a lot of vectors that could come off of a path in space. So they're kind of saying if you have a tangent vector and a normal vector, your acceleration vector is going to be in the same plane as is defined by those two other vectors. All right, and then what is that? So the tangential and normal components of acceleration. If r is the position vector for a smooth curve C, for which the normal vector exists, then the tangential and normal components of acceleration are as follows. The tangential component of acceleration is the derivative of the magnitude of v, where lowercase v would be r prime, which can be also gotten by taking the dot product of a of t times the unit tangent vector, which can also be gotten by v dot a over the magnitude of v. Okay, wow, those are equivalent? I mean, I guess I'll go with that. Depending on how long this video gets, I may prove it, or I just may wait and prove it to you in class, but we'll see. And then if you want the normal component of acceleration, that's the magnitude of your velocity vector valued function times the magnitude of the derivative of your unit tangent vector, which can also be gotten by a dot n, or the magnitude of v cross a over v, or the magnitude of a squared minus a of t squared. Okay, has a lot of options, and those options don't even really look that much alike. So let's kind of try to figure out, all right, what are we going to do with this? Well, what I could do is just kind of do it and see where it leads us, and that's what I'm going to do. So this says find the tangential and normal components of acceleration for the for the position vector given by r of t is that thing. Pardon me. And there's an awful break in line here, so I'm going to rewrite r of t in component form as 3t negative t squared. And they want me to get a sub t and a sub n. I mean, all right. Well, before I get that far, you know what I didn't say when I'm looking up at this box? Look at a sub t and a sub n. Notice how they're not bold. A sub t and a sub n, the normal and tangent components of acceleration, are numbers. They are not vectors. Okay, so that's one thing I do want to talk about. They are definitely not vectors. They are numbers. And so if I want to calculate that stuff, I mean, let's just start somewhere. Let's see which one I want to use here. If I want to find the tangential component of acceleration, I can do any one of these things. Well, I got to be honest, if I can avoid using t or n, I usually do because there's a lot of division in there and it gets kind of obnoxious. So if it's me, I'm either going to do the derivative of the magnitude of velocity, or I'm going to do this dot product. And if it's me, I'm going to do the dot product. Okay, this is probably the easiest thing to work with because then all I have to do is calculate some derivatives for vector valued functions and then divide by one magnitude. And I think that's a lot easier than taking the derivative of a magnitude, because the derivative of a magnitude would be like a big square root thing with some maybe chain rules inside. And if I can avoid that, I'm gonna. So let's find this tangential component using that last formula, v dot a over the magnitude of v. So if this is r, then v is just r prime, and that's going to be 3, -1, 2t. Okay, I'm supposed to dot that with a. Well, I can find a because a is just v prime, which is 0, 0, 2. Oh gosh, that's so satisfying. So many zeros. And now I have to do v dot a over the magnitude of v. Well, that's not a big deal. So a sub t is v dot a over the magnitude of v, which is going to be 4t, divided by the magnitude of v, which is 9 plus 1 plus 4t squared. That's the sum of the squares of the components of v. And so a sub t is 4t divided by the square root of 10 plus 4t squared. Cool. I mean, I don't know where that really does yet, but we'll get to that. So now let's find out the normal component of acceleration. Okay, so I got a bunch of options here. I could, if I wanted to go with vector form, do v cross a divided by the magnitude of v. Or I could do the magnitude of a squared minus the magnitude of a sub t squared. You know what? I'm going to do the v cross a and kind of stick with our format that we've got going right now. So I need to do v cross a, and since these are stacked right here, I'm going to figure out v cross a right over here. So v cross a is going to be -2 minus 0, and then 6 minus 0, and then 0 minus 0. Okay, so then my normal component of acceleration is the magnitude of v cross a divided by the magnitude of v, which is going to be the square root of 4 plus 36, divided by the magnitude of v, which is 10 plus 4t squared. So a sub n is the square root of 40 divided by the square root of 10 plus 4t squared. And I'm not even going to simplify that numerator. I'm just going to leave it. I mean, okay, cool. So those are my tangential and normal components of acceleration. Now, let's talk about the picture here for a second. So let's say I have a path, all right, and this is my path, okay? And let's see, that path doesn't have any arrows on it, but it really should, and I can tell which way they're going because my unit tangent vectors are pointing up, so I know that this goes in that direction. And so if I know that it goes in that direction, what I really want to figure out from here is, okay, here's my unit tangent vector. Yep, that makes sense. Here's my principal unit normal vector, which always points toward the concave side of the curve. Yep, that feels pretty good. And then this right here is the acceleration vector. This is this thing right here. Okay, so that arrow represents that acceleration vector. And if I want to know the tangent and normal components of acceleration, what that's giving us is that is giving us the length, let's see, the length of this and that. So this would be, this length right here would be the length a sub t, and that pink length right down there is going to give me the length for a sub n. All right. And the other thing you should notice is that your acceleration vector points in the same direction as your principal unit normal vector. The acceleration vector points inward toward that like centripetal force. So that, my friends, is what we have. All right. I'm going to call it quits here because I feel like this video is long enough, and you will get another video tomorrow about one of my favorite things in this unit. This unit has two of my favorite things. Projectile motion, so I can talk about, baseball and football and sports and stuff like that. And then two, we're going to talk about curvature next, and that's super cool. So everybody have a great day, and I am signing off.